The most silent residential wind turbine ever created operates on ancient Greek geometry, yet the energy it promises is a complete fabrication. Back in 2006, a patent filed in the Netherlands locked down the actual mechanics. This deception isn't buried in a thick manual. It's plastered right on the front of the packaging in a single, misleading sentence. The creators of the Liam F1 state their device harnesses 80% of the Betz limit. We are going to refer to this as the 80% illusion. Let's break down what the Betz limit actually means. In 1919, a German physicist by the name of Albert Betz established one of the most elegant principles in fluid dynamics. He mathematically proved that absolutely no rotor, regardless of its shape, can capture more than 59.3% of the kinetic energy from a moving column of wind. Expressed as a fraction, it's exactly 16/27. This isn't some arbitrary target for engineers to shoot for. It is an immovable law of conservation. The logic behind it is perfectly straightforward. If a turbine were to absorb 100% of the wind's energy, the air exiting the back of the blades would completely stop. Consequently, the fresh air blowing in would be blocked. The entire airflow through the device would halt, and your power generation would instantly drop to zero. The absolute most any device can pull from the wind while allowing the breeze to keep flowing is precisely 59.3%. Not a standard fan, not a helical design, nothing. Now pay close attention to the sleight of hand in that marketing claim. The promotional material declares the Liam F1 achieves 80% of that maximum threshold. An everyday consumer reads that and thinks, amazing, 80% efficiency. The mathematical reality is 80% of 59.3, which equals exactly 47.4%. That is the actual maximum efficiency they are claiming. The space between that figure and the inflated number buyers think they're getting is the core of the 80% illusion. But even that 47.4% is a pipe dream. Third-party field evaluations from Pusan National University in South Korea, along with Dutch testing facilities that have been monitoring these specific spirals since 2016, reveal a much harsher truth. The actual coefficient of performance hovers around 25%. That is half of what the promotional sheet suggests, and only marginally better than a properly engineered traditional turbine. Let's crunch the numbers on yearly output. The formula for available wind power is 1/2 times air density, times the swept area of the rotor, times the performance coefficient, times the wind speed cubed. If you input the Liam F1's 1.77 square meters of area, a grounded performance coefficient of 0.25 and standard sea level density, you can work backward to find the wind velocity needed to hit their advertised 1,500 kilowatt hours a year. The result is 8.6 meters per second, or roughly 19 miles per hour. That is the constant average wind speed required to make their math work. In a standard neighborhood setting, your actual yearly harvest is going to be about 400 kilowatt hours. Generating 1,500 kilowatt hours demands a relentless 19 mile per hour average gale. You are not going to experience that on a suburban roof anywhere in the lower 48 states, unless you live on a handful of extremely unprotected coastal cliffs. If you multiply 400 kilowatt hours by an average rate of 15 cents, the Liam F1 puts about $60 back in your pocket annually. Factoring in the $5,000 to $7,000 installation cost, your return on investment stretches out to almost 100 years. In practical terms, it never pays for itself. This is the point where the 80% illusion transforms from a marketing trick into an excuse for poor engineering. Because even if the box displayed accurate figures, a much more urgent problem arises the minute the power grid collapses during a massive winter blizzard. That problem hits a physical barrier that no wind-catching device in existence can bypass. Think of it as the blackout barrier. Imagine a severe winter storm has just battered your region. There are 2 feet of snow on the ground, the wind is howling at 30 miles per hour, and the power company estimates you'll be in the dark for at least 3 days. You've got a Liam F1 mounted on your roof and a bank of lithium iron phosphate batteries sitting in your basement. The sales pitch guaranteed you 90% energy independence. But the laws of physics do not read sales pitches. Every single wind generator is bound by a strict capacity factor ceiling. Capacity factor represents the fraction of power a turbine practically generates over 12 months compared to what it would make if it ran at maximum capacity nonstop. Inside a flawless wind tunnel, a 1.5 kilowatt unit could pump out upwards of 13,000 kilowatt hours a year. Out in the actual environment, it manages maybe 10 to 15% of that theoretical max. That leaves you with an average continuous output of 225 watts for a residential setup over the course of a year. When you fire up a modern cold climate heat pump, it demands anywhere from 1,500 to 3,000 watts instantly. That is 6 to 13 times the power your roof turbine can supply on its most productive week. So what exactly does 225 watts power during an extended blackout? It can keep a standard refrigerator running, since the compressor cycles on and off, averaging around 150 watts. It can handle a standalone chest freezer. It will power a few high-efficiency LED lights. It will easily charge a laptop and your smartphones. Combine those, and you get an illuminated house, unspoiled groceries, and a connection to the outside world. What it absolutely cannot provide is warmth. It won't run electric baseboards, it won't power your heat pump, it won't heat your water tank, and it certainly won't fire up an induction cooktop. Those appliances require a totally different scale of physics entirely. There is a slight seasonal advantage. Frigid winter air is roughly 10% heavier than warm summer air, and the energy contained in a gust of wind increases proportionally with that density. For every single watt you capture during a July breeze, you'll harvest about 1.1 watts from an identical breeze in January. The system genuinely generates more electricity exactly when the grid is most vulnerable to failure. However, that capacity factor ceiling remains locked in place. Air density plays a minor role. The actual bottleneck is a completely different phenomenon, which explains why not all home wind setups fail for the same reasons. The truth is, the reason the majority of these installations end up as $6,000 roof decorations isn't a flaw in the turbine itself. The culprit is the specific blanket of air hovering right above your shingles. Scientists refer to this as the boundary layer, and it creates a specific hazard that triggers 3 distinct problems simultaneously. Let's call it the boundary layer trap. Air currents do not flow smoothly right above the earth. The friction created between the static ground and the rushing atmosphere chops the lowest section of air into a turbulent mess, and this messy zone extends roughly 500 feet into the sky. Within this space, wind velocity is dictated by a power law. It decelerates rapidly over structures and trees and maintains better speed over flat water. An established rule of thumb among wind technicians is that doubling the height of your tower boosts your functional wind speed by about 15 to 30%. The issue is that the average homeowner mounts their device barely 10 feet above their roof peak, placing it squarely in the most violently turbulent airspace a structure can generate. That violent turbulence triggers the first problem. Standard 3-blade designs operate on aerodynamic lift, which is the exact same force keeping jumbo jets aloft. To create the pressure difference required to turn a rotor, lift relies entirely on clean, uninterrupted air gliding over the blade. The second that airflow becomes choppy, unpredictable, and shifting, the pressure difference evaporates. The blades stop generating rotational force and simply begin to vibrate. That vibration leads right into the second problem. Every traditional turbine operates with a specific tip speed ratio, comparing the velocity of the blade's outer edge to the speed of the incoming breeze. To hit maximum efficiency, lift-dependent blades need a tip speed ratio of around 6 to 8. In a modest 11 mile per hour breeze, the outer tips of those blades are already ripping through the air at 60 to 90 miles per hour. Moving at that velocity, every single blade tip trails a swirling vortex of air behind it, creating that repetitive thumping sound that drives neighbors crazy. But those vortices aren't just an acoustic nuisance. They represent raw, kinetic energy being carelessly discarded into the atmosphere. Every vortex contains the exact force that was supposed to drive the generator, squandered as turbulence spinning off the edge of the blade. Out in wide open, high wind environments with smooth air, that penalty is negligible. In the chaotic wind of a suburban neighborhood, it ruins the system's efficiency. The third problem is orientation. A standard 3-blade unit must constantly point directly into the wind to function. When the breeze changes direction, an internal yaw motor engages, physically rotating the heavy turbine head to face the new current. That motorized movement requires electricity. In an urban environment where the wind direction zigzags every few moments, that yaw mechanism can easily draw more power than the blades are actively generating. What you get is a machine that looks like it's working, while secretly siphoning energy straight out of your battery bank. Combine those 3 factors, and the reality is undeniable. Strapping a traditional 3-blade turbine to a residential roof does not give you a power plant. It gives you an expensive, vibrating lawn ornament pretending to be a generator. This exact hurdle is what an engineer from the Netherlands conquered in 2003. He didn't do it by tweaking the propeller. He did it by abandoning the concept of propellers entirely. The mechanism he engineered is now known as the Archimedes Reversal. He had been studying the ancient texts of Archimedes when he spotted an overlooked application of Greek geometry. Back in the 3rd century BC, Archimedes had figured out the volume of a 3-dimensional helix, and applied that math to invent a water pump. One person manually cranking a spiral screw inside a tube could pull massive volumes of water directly against gravity. This invention was utilized in Egypt to pull water from the Nile for farming, and the Romans later used it to pump flooded subterranean mines dry. For over 2 millennia, the Archimedes screw stood as the ultimate mechanical solution for lifting liquid. The Dutch inventor flipped the premise with a very basic question. If rotating a spiral can push water, could moving water rotate a spiral? He built a prototype, placed it in a flowing stream, and the water successfully turned the screw. That led to the ultimate question. If water could do it, could wind? By 2006, the first functional models were submitted for patents. Following 10 years of rigorous outdoor testing and tweaks, commercial manufacturing kicked off in 2016, resulting in the Liam F1. The shape that powers this device has nothing to do with the Fibonacci sequence that marketing teams love to reference. It relies on seamless, distributed pressure integration. As the wind flows directly into the cone, the spiral geometry forces the air to execute a 90-degree turn as it travels through. Instead of a sharp pressure drop across the razor-thin edge of a blade, the pressure differential applies across the entire contained volume of the helix itself. This widespread pressure seamlessly transforms straight-line wind momentum into rotational momentum, without any sharp blade tips to create wasted vortices. This specific shape delivers 3 massive advantages. First, it automatically tracks the wind. Because the helix is perfectly symmetrical along its spinning axis, it naturally pivots to face the strongest airflow without relying on a power-draining yaw motor. Second, it can capture wind approaching from up to 60 degrees off-center, meaning the swirling, unpredictable gusts found on rooftops won't cause it to stall out. Third, it starts generating usable electricity in winds as low as 5.6 miles per hour, essentially half the starting requirement of a standard propeller turbine. And since it lacks blade edges, it produces zero-tip vortices. Operating at maximum capacity, the whole assembly registers under 45 decibels, softer than a normal talking voice and quieter than a gentle rainstorm. Its leisurely spinning motion also makes it highly visible to birds, rather than becoming an invisible high-speed hazard. After 10 years of data collection in Holland and Korea, the mechanism has proven to be incredibly safe to operate. However, none of these engineering triumphs mean this spiral can take your house off the grid. What it signifies is that the complex physics of harvesting electricity from turbulent city air was successfully cracked, proven in the field, and then completely ignored by the North American market. The failure wasn't in the science. It was a breakdown in the supply chain. That brings us to the next critical topic, which has nothing to do with the turbine hardware. It's about the one vital calculation you absolutely must perform before spending a dime. The entire feasibility of installing one of these systems relies on a procedure we'll call the cube law audit. The sheer energy contained within the wind scales exponentially with the cube of its velocity. A 9-mile-per-hour breeze isn't merely 30% weaker than a 13-mile-per-hour breeze. It contains roughly 2/3 less energy. The cube law is the absolute governing force of home wind generation, and it's the one formula the manufacturers conveniently leave off the packaging. Before you even purchase a spiral turbine, you must install an anemometer at the precise spot and height you plan to mount the unit. You need to record the wind data for at least 3 months. 6 months is vastly superior, and a full 12 months is ideal. To make the economics work, your location needs to maintain a consistent average wind speed of at least 10 to 11 miles per hour. If your site falls below that average, the unforgiving math of the cube law destroys any chance of a return on investment, regardless of how brilliant the rotor's design might be. Your mounting elevation is just as critical as the wind speed. The device must be placed a minimum of 10 to 16 feet higher than the tallest peak of your roof or any surrounding structures upwind. If you drop it down into that turbulent boundary layer, the wind velocity plummets by 30 to 50%. When you apply the cube law to that drop, you are looking at a devastating 70 to 90% loss in total power generation. If you pass the audit, the required equipment list is brief but absolute. The standard residential model is the Liam F1, running between $5,000 and $7,000, which includes the mounting hardware and the charge controller. If you are outfitting a tiny off-grid shack, the smaller AWM 750D outputs 150 watts and will set you back around $2,000. Do not buy the inexpensive plastic knockoffs flooding online marketplaces. They share no engineering DNA with the genuine article and will shatter in a matter of months. The wiring phase is where the majority of DIYers ruin their systems. You absolutely must use a wind-specific maximum power point tracking charge controller. Standard solar controllers will fail because wind generates power in erratic, surging pulses that a solar computer interprets as a system malfunction. You also require a dump load, a dedicated bank of thermal resistors designed to burn off excess electricity as heat. If a massive gust hits when your batteries are totally full, that dump load gives the turbine a place to send the energy. Without it, the rotor would spin freely with no resistance, accelerating past its structural limits until it destroys itself. When it comes to battery banks, lithium iron phosphate is the only viable option. Traditional lead-acid setups simply cannot endure the aggressive fluctuating charge cycles that wind power delivers. When you run this system alongside solar panels, the wind turbine does its heaviest lifting at night and during the winter, the exact periods when your solar production tanks. Integrating both technologies can elevate a home from 60% self-reliance on solar alone to an impressive 90% true hybrid independence. Routine upkeep is minimal and tied to the seasons. You check the central bearings annually. You inspect the spiral for accumulated ice or debris, as extra weight can throw the Helix out of balance and transfer damaging vibrations down into your roof mount. You also test the emergency mechanical brake once a year to ensure it will physically stop the blades if the electronics fail during a severe gale. But when the neighborhood goes dark, the most difficult challenge isn't keeping the rotor spinning, it's figuring out how to store substantial energy for an extended outage. And the most cost-effective method to stockpile that wind energy during a blizzard isn't a wall of lithium batteries. It's a $300 barrel of sand that can trap and hold 6 weeks' worth of heat without a single microchip. We'll break down exactly how that works in the next video.